Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
Hi, everybody, and welcome back to Bufnagle the podcast, where we talk about all things good in the pursuit of the adventure of life. I'm Rafe, and Podcast Tuesday means it's going to be a great Podcast Tuesday, as we attempt to do every week. So, hey, you guys are the reason we are a global top 10% podcast. You are the world's greatest listeners, as you all know. You can reach us, as is typical, at bufnagle@bufnagle.com. Remember, share the love, share the buff, give us a 5-star review, subscribe, like, do all those things in your life that make my life better, and that will in turn make your life better as well. Remember to tell a friend to listen, and you will get a free episode. And somewhere buried in the show links, if you can find it, is a link to buy me a coffee or whatever. At this point, we'll take pretty much anything. Hey, these are some thoughts, okay? These are some thoughts about the mean. And hang with me here. This is not just, this is not ninth grade algebra here that we're going to be discussing. We're going to cover a lot of things that all kind of came together at once for me over the last several days. And I did some reading, some research about a book, read some stuff. And I put a number of things together that I've been thinking about for quite a while. And it comes to a head today here at the Buff. All right. You heard it here first. Unless you heard it somewhere else, then you heard it there. I'm a statistician. So I was trained in that. I have my undergraduate degree in mathematics and my graduate degree in statistics officially, not data science, not biostatistics, not machine learning. It is a good old-fashioned statistics degree, which means we learned a lot of stuff that they don't bother learning anymore. But I think they come back. Those things come back. When you get older, you realize that they were probably pretty valuable. Most people think that when I'm a statistician, that means I spend a lot of time computing statistics. I do. I spend a lot of time on my calculator. When we used to play golf, we'd be out there and someone would say, hey, you're the statistician, you keep score, as if I was somehow better at writing the numbers in a little box on a cardboard card I keep in my back pocket. Or they would ask me things like, oh, you're a statistician, really? Okay. Who won the 1955 American League batting title? And I would reply with, of course, it was Al Kaline who batted .340 that year for the Tigers. But most statisticians don't memorize statistics, all right? So most of the statisticians people run into are when you watch the ball game and they'll come up with some obscure fact, like only 6 times in the history of the world has a team been down by this many runs at this point in the game and come back to win it in extra innings while hitting a home run left-handed on a Thursday or something. They'll come up with something like that, and they call that job of database digging typically is assigned to someone who has the title of statistician. But people like means, okay? People use that all the time. They talk about averages, and I have computed my share of means in the past, and that's the topic of this episode really is means. Things like mean blood pressure, the mean time to event, maybe watching for for a subject to die or a subject to get an event or a subject to be healed or something like that. You could have the mean price of gas at the gas station in July, there's people love means and they love them for a reason. And that's part of the discussion today. So, percentages are actually means. They are means. If you code yeses as ones and nos as zeros, you get means. And I think they love means because that's all they hear about, right? We hear about mean, the mean age at which you get your first job, or they talk about the mean age when you get married, or the mean salary, or people talk about means because they think that that's what they're supposed to do. And the reason they think that is because that's what they learned in stats class when they took that one stats class on, Monday, Wednesday, Friday morning in college. And they really loved it because it was 9 o'clock in the morning and that wasn't the kind of class they really liked on a Friday. So anyway, we taught them that. We taught them the mechanics of being a statistician. And there are interesting things about the mean, even though that's all that people know. But we're going to talk a little bit more about how to think about them. And that's going to lead us to somewhere where you never thought this was going to go. So we talk about means or averages, or, in reality, most of us talk about the arithmetic mean, which is, here's the math lesson. You take all the numbers you have, you add them together, and you divide by the number of numbers. So if you have if you have two numbers, you have 2 and a 6, then the mean of that is 2 plus 6, all divided by 2. So you get 8 over 2, which is 4. And the mean of 2, 3, and 7 is 2 plus 3 plus 7, which is 12, divided by 3, which gives you 4. And there's some interesting things about the mean that you can, these are the kinds of things you can do if you take upper level math classes. You prove things like the mean is always bigger than the smallest number in the group. And it's greater than or equal to the smallest number in the group. And it's always greater than, or it's less than or equal to the largest number in the group. So it's between the min and the max, we would say, inclusive. If you were to take your data and plot them on a number line, put a little dot, a BB, a weight 1 at each data point, if you would put a little weight there on a balance beam, you would find that balance, that beam will balance at the mean. That point where it balances is the mean, and you can demonstrate that using physics kinds of things, or you can do some other, draw some vectors and things like that and get it to go. You can show that the sum of deviations from the mean is 0. So if you take all your data and you compute the mean, and then you compute the distance from every data point to the mean, right? That distance is the value minus the mean, or the mean minus that value. Because you got to go always in the same direction, because some are negative and some are positive, right? You got to take care of that negative sign there. But if you do that and you sum up all those deviations, you will get 0. And that's not a difficult thing to show. But if you've never done that sort of thing, it's you might not even know where to start. So if you really want to know how to do that, well, give me a call. We'll do a personal over the phone special bufnagle proof over the phone. We will prove to you that the sum of deviations from the mean is 0. You can also show that the sum of the squared deviations from the mean is smaller than the sum of the squared deviations from any other number. Okay, so we say that the mean minimizes the sum of squared deviations. So it's kind of it's a good point to think about, kind of like a middle point of a set of data that you have. Okay, so there's reasons why you would be interested in using that point as kind of a middle point. The arithmetic mean does that, but there are other kinds of means, and this is where you're probably hoping that your commute is short and you get to shut this episode off pretty quick. There are other episodes. There are other different kinds of means. There's the geometric mean, which is the nth root of the product of the number. The geometric mean, for example, of 4 and 64. Okay, somebody gives you a 4 and a 64. You take the square root of 4 times 64, which is the square root of 256, which is 16. Now, I use the numbers 4 and 64 in this example because there's a little trick I'm doing here. 4 is 2 to the second power, and 64 is 2 to the sixth power, and 16 is 2 to the fourth power. And if you take the average of 2 and 6, the arithmetic mean of that, you will get 4, and 16 is 2 to the fourth. So the geometric mean it can be found from the exponents, from the arithmetic mean of the exponents. Okay, so you can do things with logs, geometric means. Geometric means live in the world of multiplication. Arithmetic means live in the world of addition, and you can map one to the other using logs and exponents, and everything lines up. There's a mean called the harmonic mean, which is the reciprocal of the mean of the reciprocals. So if you take the reciprocal of all your numbers and you average them, and then you invert that, you reciprocalize that, you will get the harmonic mean. And you may say, well, that seems like a kind of silly thing to do, but it turns out that you use that in some algebra problems. If someone asks you, you drive from point A to point B at 55 miles an hour, And then as soon as you get to point B, you turn around and you drive back at 65 miles an hour. What is your overall average speed? And you're tempted, if you are like most people, you are tempted to say, well, the average 55 and 65 is 60. So therefore, I think the average speed will be 60. And it turns out that's not the case. The average speed you have to compute by that nasty formula, distance equals rate times time. The overall average speed, you can compute this. You can do this math. The rate is whatever the distance is. It's twice the distance. Right? That's the total distance divided by the time, and the time is going to be d over 55 for going from A to B, and it's d over 65 when you come back. And those d's all cancel out, and you get 2 over 1 over 55 plus 1 over 65, which comes out to be 59.583 and change. So it's a little less than 60 miles an hour. And the reason it's less than 60 miles an hour is because you spend more time driving at 55 than you do at 65. And so, that's a thing. And it's kind of a cute little problem. But harmonic means show up there. It also shows up in some other places wherever you have these kinds of distance, rate, and time problems and some things like that. It shows up in statistical sample size calculation for when you're working with unequal sample sizes, fixed ratios of sample sizes, you get harmonic means floating in there. So the point is, there's lots of different kinds of means you can do. Most of the time, people mean the arithmetic mean, but they may mean geometric mean. We just demonstrated that they're kind of related, depending on if you're living in a multiplicative world or an additive world. So you got means, okay? And people use means to this is in air quotes, these little finger quotes here, to represent a group by a single number. Okay, so you have a bunch of numbers. You have maybe a bunch of people that have a measurement on all them. You have a bunch of rocks that have a measurement on them. You have a bunch of houses that have a measurement on them, and you want to represent the group with a single number. Okay, so here's an example that came actually from back when Zach was in fourth grade. I think this was. He had a homework problem, and they had it was some sort of how they have fourth grade problems to help you understand. They're really just riddles with in a math sense, but they find the mean of here's 4 numbers. It might have been here's 4 kids in the class, and they each have a certain number of pieces of candy in a bag or something like that. And so the question basically was what's the average number of pieces of candy per kid, right? And the numbers, those of you who are driving, you make sure you write this down on the dash as you're doing this. So the numbers are 2, 2, 3, and 9 are the 4 numbers. And this says essentially find the mean of those numbers. Okay. So the first question was find the mean. The second was find the median. And then the third question was if you could use, if you had to use one number to represent this set of data, which number would you use? Okay. So the mean is 2 plus 2 plus 3 plus 9, which gives you 16. Divided by 4 is 4. And I remember Zach did that work. It was in the 4th grade. I don't know if they used a calculator or if he just knew that 16 divided by 4 was 4, but 2 plus 2 plus 3 plus 9 is 16. Divided by 4 is 4. And he said, I got 4 for the answer. And I said, he said, is that right? I said, yes, that is the right answer. 2 plus 2 plus 2 is 4, plus 3 more is 7, plus 9 more is 16. 16 divided by 4 is 4. Yes, you got the right answer. And he said, I'm worried I was worried that wasn't the right answer because 4 isn't one of the numbers. That was his statement. And, I was a grown adult at this point. I got a big fancy degree in statistics and, I'm pretty good at computing means, adding things up, dividing by 4. That's right in my wheelhouse. I said, Zach, yeah, I'm pretty sure that's right. 16 over 4 is 4. And he said, but Dad, that's not one of the numbers. Why would I use that number to represent a group? That's what he said. And I remember at that time thinking, well, that's a really good question. And even the premise of the question that was asked of him in that math assignment was a silly question. And the question was, if you could only use one number to represent that group, would it be the mean or the median? And they're supposed, what you're supposed to do is you're supposed to calculate the median. The median there is 2.5. It's halfway between, you write them in order, 2, 2, 3, 9, and you take the midpoint between the two middle guys there, between 2 and 3, and you get 2.5. And that's the median. And he learned that when you have a data point that kind of sits outside of the other ones, in this case, the 9 is if you draw a little dot plot, put a little X on your paper everywhere there's a number, you have the 2 and the 3 are really close together, and the 9's way out off on the right. And so he was trained to say when there's an outlier, you're supposed to use the median. And I think my response at that point was, this is a really stupid question, because you only got 4 data points, right? Why can't you just write down 2, 2, 3, 9? Those are the numbers: 2, 2, 3, and 9. You can draw a little dot plot, put little dots on the number line. There you go. There's the whole group. And there's no gun to my head saying you have to pick one number to represent this whole group. And like he argued, 4 isn't even in the group, so why would I use 4? 2.5 isn't even in the group. Why would I use 2.5, even if there is an outlier? Like, why don't I just write down all the numbers? And the answer is, yeah, you should just write down all the numbers. Right? Why do you use the mean? Well, you can go around and around on why you use means, and there's some statistical reasons you might do that. But the point is, there's really no gun to your head on how you have to summarize that. And to do it with the mean is, just as good as doing it with the median, because they both suck. Okay, that's the general thing there. If we have 2, 2, 3, 9, you ought to write down 2, 2, 3, 9. Say these are my numbers. And we'll get back to more on that in a little bit. So those were the first 2 things that popped up about numbers and means. And the first one was, like I said, you're a statistician. You do statisticianing things. And the second was this story from Zach's youth. And then the third one was this a story I read. I read it on the LinkedIn machine. Somebody had linked to it because it's LinkedIn, right? It's linked. All right. Somebody, and basically the story goes like this. It's one of these things, one of these dramatic retellings of these brilliant business insights that you see on LinkedIn, where people post these things probably as an effort to stay relevant, right? So the story apparently comes from Amazon. And Amazon is a very big company and has had tremendous success, and they do a lot of things great. They do some things people don't like, and you may like or dislike Mr. Bezos, but that's just he did the thing, did the work, and now he's got a company named after a big river or a big area in South America. So Amazon has metrics for wait times, or they did at the time, for when you call the help desk, or whatever, you call, your book's missing, or you ordered something that didn't show up, it was the wrong color. Back in the day, you could call the thing. And apparently there was a meeting with Bezos and his underlings, and the guy in charge of the call center was, hey, Tim, how's it going over there in the call center? And the guy said, well, it was great. Everything was wonderful. Our average wait time was less than a minute. And Bezos apparently had access to, I guess you call it, customer complaint emails, and people were complaining a lot about the call wait time. And he thought that sounded like it wasn't all well. Things seemed like there was a little bit of hooey going on there. So Bezos, in the middle of the call of the meeting, he reached out to the speakerphone and he called the 800 number for Amazon. And it rang, 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 and it rang. That's the whole story. And it goes on. Apparently it was over 10 minutes. It was over 10 minutes before anybody picked up. And I don't even remember in the story if anybody ever picked up on that call. And the issue, the question was, or the statement that you're supposed to learn from that is like, sometimes if the numbers you're reporting don't fit the anecdotes that you hear through the grapevine or through what customers are saying, then it's probably your numbers that are not quite telling you what you think. So the department was reporting that average wait time, was recording the wait time for calls that were answered. And you can see the issue here, right? If you call and you wait 35 minutes and it never gets picked up and you don't include that datum, then your means, you're not reporting what you think you're reporting. And I keep thinking of this, of the scene in The Princess Bride, where the guy who thinks he's really, really smart, he says, he keeps saying inconceivable. And finally in what's his name? Inigo Montoya says to him, I do not think that word means what you think it means. You keep using that word. I do not think it means what you think it means. And in data analysis, we used to always have a phrase that a lot of times you report numbers, but I do not think that number means what you think it means. And if they are reporting the mean of all the calls that were answered, that's going to give you a different number than the mean wait time for all the calls, even the ones that weren't answered. Now you could ask the question, well, if it never got answered, what's its time? And I say, well, I'll tell you the time. Time is at least as long as it rang. And I've worked with call center data, and it is a fascinating study. And we'll go into that sometime later. If you want, we'll do a private bufnagle thing. Give me a call and we'll talk about that one. So at Amazon, the thing that they were measuring, the datum that they were reporting, the mean, that wasn't a good measure of the satisfaction of the call center. Okay, so the mean may not mean what you think the mean means, and we used to say, "What does the mean mean?" And that's a very important question. Now, what the statistician likes to think about, and this is all getting relevant to one of these things that what do we say? All things good in the pursuit of the adventure of life. This is one of these things, and when we look at data, what we really want to understand is what statisticians call the distribution, which is kind of it's a what I'll call it an academic concept that compares how often what things can happen with how often they do happen. Okay. And the things that can happen, statisticians call that the support set. That's just the list of outcomes. And then the frequencies, how often they do happen, that's called the mass function. So typically we will draw a little XY plot, and on the x-axis we will put the outcomes. So I might put on the x-axis I might put number of pieces of candy, okay, and on the y-axis I will put the frequency. So for 0, I will put there's nobody had 0, nobody had 1. 2 people actually had 2 pieces of candy. 1 person had 3 pieces of candy. And 1 person had 9 pieces of candy. Okay, that's a little dot plot. It can be a histogram. You can draw a cumulative distribution function. Lots of ways to describe that. But what really matters is this relationship between how often a thing happens and what can happen. Okay, so that question, how often does this thing happen relative to the other things that happen? That's the question we should ask about data. Okay, 2 kids had 2, 1 had 3, and 1 had 9. I can't imagine there were only 4 kids in the class. That might have just been the kids with candy. Maybe there was 28 kids that had 0. Sometimes those get left out. So those are questions that statistician and data people tend to ask about that. Okay. So there's 2 questions is how often does this thing that I'm interested in happen relative to all the things that can happen? And then the other question is what causes some of these kids to have none, some to have 2, some to have 3, and 1 have 9? What's the cause of that? Is the kid that have 9, is that the kid whose parents own the candy store, or are the 0? These are all the kids that just came back from the dentist. I mean, what is the source of the variation? Okay, and that is those are fundamental stats questions. So to just have, those are the things that should be investigated when you're doing data analysis stuff. Okay, so note that those 2 questions, how often does this happen relative to the other things, and what's causing the variation, neither of those questions is answered with the mean. Neither one is answered with the mean. In fact, the things that people want to ask, the mean very rarely shows up for things that people really want to know. You may ask somebody something, and they may answer you with the mean, but that doesn't really tell you what you want to know. And not only that, it doesn't tell you what you want, but it actually it masks the uncertainty in your understanding. Okay, the mean doesn't answer the questions, and it masks the uncertainty, and it actually works against you knowing what you want to know. Okay, so if I read a study, I worked in clinical trials for 100 years, and if I read a study and says the average age of the patients in the study was 50 years old, I may say that in the abstract or in the list of demographics or whatever it is. I may say average patient was 50 years old, blah, 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 right? Average patient 50 years old. Well, what does that mean? The patients are 50 years old? Is that what that means? Well, it doesn't mean that. It means that on average they were 50, but it doesn't really tell you anything. I could have a bunch of patients. I could have half the patients at 40 and half at 60, and it could mean at 50. I could have half of them at 49 and a half and half at 50 and a half, and still the mean is 50. All right. So what does that mean? And the answer is it doesn't really tell you what you want to know. Okay. You may seek all sorts of things from the data, or you may ask questions like how many of these patients are approximately my age, whatever that is. In my case, it's 60, but in your case, it might be 25 or might, and then you can judge from that how relevant the patients are to what you're going through. How many of these How many of the patients are children? How many of the women in the study are postmenopausal? Maybe that matters. Okay. How many of the patients are over age 80? When you get old, things happen to you that, you are different. Okay. But the really important question that I really, really want to know with regard to whatever I'm studying in age there is, how does age impact the thing being investigated? Okay. Whether it's heart disease or high blood pressure or vaccine effectiveness or whatever. Okay. And reporting mean age in that context is absolutely useless. Could be. And the reason is, it's not because it's not maybe interesting, but it doesn't answer the questions that you want. It's useless because you want to know about the individuals in the study, right? I'm telling you that the average age is 50, which doesn't tell you anything about the individuals. It tells you when you take all their ages, add them up, and divide by the number of people you have in there, you get 50. Okay. So what I really want to know is about the distribution. Okay. I want to know all the things that can happen. Give me a list of what can happen and how often they happen. And what you're probably going to find is you're going to have, if you plot that little thing in histogram, it might kind of bell-shaped, it might be kind of skewed one way or the other, and all these words that you learn in your stats classes. But the mean doesn't get you where you want to go. Unless you want to compare one group to another group, you can compare the means, but you're really not even comparing the individuals. Okay? And the mean has some very nice properties in a theoretical respect, and that's what we're going to get in just a little bit. But it doesn't tell you It doesn't tell you what you want to know, which is, tell me about the individuals in the population. Okay, now populations and samples, that's something statisticians talk a lot about. There's maybe, in theory, you imagine there's this big group of people of which you're going to pull a little group out of that. And there are very nice things that happen with that. The population may have a mean, and the sample has a mean. And if you take a different sample, it has a different mean. But if you take bigger and bigger and bigger samples, then that mean for that one converges to the mean of the population. There's central limit theorem, all those things going on. But that may be interesting that the sample mean converges to the population mean. But you know what? I'm really not interested in the mean. I'm interested in the individuals. Okay, so all this leads to part D here, the fourth one, which is a post I read last week by Andrew Clavin, and it was from Carl Jung, the Swiss psychiatrist, in a little very very little book. It's this little tiny book that he wrote called The Undiscovered Self, and I think it was published in 1959 or so. That's 1957. 1957, 1958 is copyright. And he was, like I said, a Swiss psychiatrist. He was the founder of analytic psychology. And in this book, The Undiscovered Self, he pokes, among the things he does, is he pokes at the problem of using population models to try to develop self-knowledge. Okay, so he talks about knowledge and understanding and how those two things are not necessarily the same. And he says, a number of quotes coming up here. He says this on page 7. Since self-knowledge is a matter of getting to know the individual facts, theories help very little in this respect. For the more a theory lays a claim to universal validity, the less capable it is of doing justice to the individual facts. Any theory based on experience is necessarily statistical. That is to say, it formulates an ideal average, which abolishes all exceptions at either end of the scale and replaces them by an abstract mean. This mean is quite valid, though it need not necessarily occur in reality. Despite this, it figures in the theory as an unassailable fundamental fact. The exceptions at either extreme, though equally factual, do not appear in the final result at all, since they cancel each other out. For instance, if, for instance, I determine the weight of each stone in a bed of pebbles and I get an average weight of 145 grams, this tells me very little about the real nature of the pebbles. Anyone who thought, on the basis of these findings, that he could pick up a pebble of 145 grams at the first try would be in for serious disappointment. Indeed, it might well happen that however long he searched, he would not find a single pebble weighing exactly 145 grams. The statistical method shows the facts in light of the ideal average, but does not give us a picture of their empirical reality. While reflecting an indisputable aspect of reality, it can actually falsify the actual truth in a most misleading way. This is particularly true of theories which are based on statistics. The distinct thing about real facts, however, is their individuality. Not to put too fine a point on it, one could say that the real picture consists of nothing but exceptions to the rule, and that, in consequence, absolute reality has predominantly the character of irregularity. Okay, so Jung is saying here, just what I was saying just before, okay? The mean can be computed from a set, but it doesn't represent the set. I mean, it kind of lives in the middle there, but there may or may not be anybody that actually looks like the mean. And not only that, when you report the mean as a piece from the center, you're throwing out all the exciting stuff in the tails, okay? All the stuff that's on the outside, you're losing that when you report this mean thing, all right? And he continues. Now, whether it is a question of understanding a fellow human being or of self-knowledge, I must in both cases leave all theoretical assumptions behind me. Since scientific knowledge not only enjoys universal esteem, but in the eyes of modern man counts as the only intellectual and spiritual authority, understanding the individual obligates me to commit, how do you say this? Let's say majestic, right? It leads me to insult the magistrate, the king, okay? It leads me to commit a crime against the king, so to speak, to turn a blind eye to scientific knowledge. This is a sacrifice not lightly made, for scientific attitude cannot rid itself so easily of its sense of responsibility. And if the psychologist happens to be a doctor who wants not only to classify his patient scientifically, but also to understand him as a human being, he is threatened with a conflict of duties between two diametrically opposed and mutually exclusive attitudes of knowledge on the one hand and understanding on the other. This conflict cannot be solved by an either or, but only by a kind of two-way thinking, doing one thing while not losing sight of the other. He is saying that if you want to really understand the individual, you have to take a chance, and you have to throw out these ideas of looking only at the center. If I want to know about the individual bags of pieces of candy that these kids bring in, I can't talk about what was the average, 4 as the average, because I can't say you guys have 4 pieces of candy, because none of them have 4 pieces of candy. Exactly what Zach, the 4th grader, said however many years ago. Just like that, you can't do that when you're looking at big pictures. And scientific models tend to do that. We tend to think of things. We got average miles per gallon in our car. We have average wait times when we call Amazon. We have average bank account balances. We have average prices of gas. And what we miss on all those things is the distribution, the big picture of the individual pieces of data, right? And I call those atomic level data, the individual pieces that make up the whole. You can have a big molecule there, a big piece together, but it's made of a bunch of little things, and we need to understand all of them, okay? Now, in view of the fact that in principle, the positive advantages of knowledge work specifically to the disadvantage of understanding, okay? Knowledge, knowing the mean gets in the way of knowing about the data, right? Knowledge works specifically to the disadvantage of understanding. The judgment resulting therefrom is likely to be somewhat of a paradox. Judged scientifically, the individual is nothing but a unit which repeats itself ad infinitum and could just as well be designated with a letter of the alphabet. For understanding, on the other hand, it is just the unique individual human being who, when stripped of all these conformities and regularities so dear to the heart of the scientist, is the supreme and only real object of the investigation. The doctor, above all, should be aware of this contradiction. On the one hand, he is equipped with statistical truths of his scientific training, and on the other, he is faced with the task of treating a sick person who, especially in the case of psychic suffering, requires individual understanding. All right, how many times you go to the doctor and you say, he said, well, here you have this cough. I want you to take this medicine. And you say, how long is the cough going to last? And he says, on average, the cough will be gone in 4 days. All right. And my thought is always, great. How long is it going to last for me? Okay. The doctor is talking about knowledge work compared to understanding. He's talking about the group as a whole instead of about the individual. And the doctor needs to be aware of this contradiction. When he reports how it is for the mean, he's not reporting it for any individual. Jung goes on, the more schematic the treatment is, the more resistance it calls up in the patient, and the more the cure is jeopardized. The psychotherapist sees himself compelled, willy-nilly, to regard the individuality of a patient as the essential fact of the picture and to arrange his methods of treatment accordingly. Today, over the whole field of medicine, it is recognized that the task of a doctor consists in treating the sick person, not an abstract illness. Okay? Pay attention to the individuals. And these grand summaries, these grand models of understanding the world that don't take into account the individuals, they don't carry the day. Scientific education is based in the main on statistical truth and abstract knowledge, and therefore imparts an unrealistic, rational picture of the world. Let me repeat that. Scientific education is based on the main Scientific education is based in the main on statistical truths and abstract knowledge, and therefore imparts an unrealistic, rational picture of the world. An unrealistic, rational picture of the world in which the individual, a merely marginal phenomenon, plays no role. The individual, however, is an irrational datum, is the true and authentic carrier of reality, the concrete man, as opposed to the unreal, ideal, or normal man to whom the scientific statements refer. What is more, most of the natural sciences try to represent the results of their investigations as though these had come into existence without man's intervention, in such a way that the collaboration of the psyche, an indispensable factor, remains invisible. Parenthetically, an exception to this is modern physics, which recognizes that the observed is not independent of the observer. So in this respect, too, science conveys a picture of the world from which the human psyche appears to be excluded, the very antithesis of the humanities. Under the influence of scientific assumptions, not only the psyche, but the individual man, and indeed all individual events whatsoever, suffer a leveling down and a process of blurring that distorts the picture of reality into a conceptual average. Now, I said that. Exactly what I said here is when you focus on the mean, you blur what you really want to understand. You see the mean and you don't see all the individuals. You see, like if you look at the individuals, you see the outliers. You see the things that are odd, the things that are interesting, the things that make the world a worthwhile place to be and a problem that's difficult to solve. Okay, he goes on. We ought not to underestimate the psychological effect of the statistical world picture. It displaces the individual in favor of anonymous units that pile up into mass formations. Science supplies us with, instead of concrete individual, the names of organizations, and at the highest point, the abstract idea of the state as the principle of political reality. Now, I'm not going to go political on this. Okay, I'm not going to, because we can take this and go all sorts of different ways, and you can go read about what Jung said about these kinds of things. But the important point here is not everything is rational. That's the important thing. Not everything has the explanation, has this, not everything lives in this world where the mean lives, okay? There are individuals and then there's the mean of the group, and those are not the same thing. If your perception of the world is solely regarding the things that are rational, then you are ignoring the fundamental, most important thing on the planet, which is man. And I'm not talking men, I'm talking mankind, humanity. You are missing that. Jung said that he called it right out. He said, man is an irrational datum, okay? But he's a datum nonetheless. So if you're going to have a model that only focuses on the rational things, that only looks at the means and doesn't look at the original, the underlying atomic level data, if you're going to do that, you miss out. And your model necessarily is faulty. Now, this is a conundrum. Okay, this is a really difficult thing because our models do these things. Okay, these scientific models that we have they make the world go around. Okay, people seem like all of our large all of the I'll call them industrial level models of the world, whether we're looking at how to adjust interest rates to help inflation go up or down, or how to set, I don't know, whatever sort of government programs you have set up. Those are all set up looking at man as a center point in a distribution. It's not looking at the individuals. They all look at the means. They all look at means, and the reason they do it is because they have to. Right? There's no other way to do it, and that's a rational model, and therefore it doesn't fit humanity. Okay. Now, I'm not saying we shouldn't do science, right? But I'm saying a science that ignores the irrationality of human beings isn't a model that is sufficient to describe what we have. Okay. So if you are using models that are only rational, you miss at least half of the human experience. Okay. It's kind of like trying to do a higher level mathematics without using the complex plane, with only using real numbers, and you can't use complex numbers. And there's all sorts of things you can't do unless you have complex numbers. So Shakespeare has Hamlet say to Horatio, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." The philosophy, the models, the fixed, rigid world of the means and the regressions and the machine learning, all this stuff, all of that lives in a world of means. and it misses all of the nuance and the edges. And there is more in heaven and earth than is dreamt of in your philosophy. There's more than that. Okay, there's the irrationality of the human datum. So, a couple points of summary very quickly, because oh my goodness, we're almost out of time. 0. You are in a population, but you are a unique individual. The mean of your group is not you. Number 1. Others are in a population, but they are also unique individuals, and the mean of their group is not them. Be cautious with summaries and look to understand the data, the original individual data atoms that underlie everything else that you're doing. You have to see things at the atomic level, because if you look only at the summaries, you miss it. It just, when you roll it up to the mean, you lose the individuals. All right. And you can't work with humanity in that way. All the fun in your data sets, for those of you who do data analysis on a regular basis, all of the fun is in the outliers. It's in the fun stuff in the tails, right? The stuff in the morning is in the middle is boring. Don't forget to look at the outliers. Okay. Don't throw them out because they don't fit. They are the things you're looking for. Don't lose the trees for the forest. Be willing to look outside of your model. You have to see what's outside of your model and be critical of that model. George Box said that all models are wrong, but some are useful. There may be uses for these models, but to really understand the nature of man, you have got to go outside of the rational models based on the mean. There are more things in heaven and earth than are dreamt of in your philosophy. Don't let that philosophy only focus on the means. Do not ignore the pieces of humanity that live outside the material realm. Remember, seek the good, live virtuously and flourish, and enjoy the adventure of life.
It's going to be a great day.